Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 18, and we are going to continue with our derivation for linear momentum balance in cylindrical coordinate system. Okay. So, recall from the last class we have this generalized cylinder here, generalized cylinder, and then we thought of a cylindrical element which we then zoom here. The picture right here is the cylindrical element, okay, and we figured out what was the force due to tractions on this cylindrical element on plus z and minus z plane, is not it. So, recall that the force on plus z plus the force on minus z due to traction, that came out to be del sigma z z over del z times E z plus del tau theta z over del z times E theta plus del tau r z over del z times E r, and the whole thing is multiplied by delta V, the volume of the cylindrical element, plus small o in delta V, the higher order terms, right. And we did a very long derivation for this, is not it. We could also derive this in a simpler way, but of course, it is an approximate way. Our derivation was exact, but there is a approximate but simpler way to derive this, which is, so instead of thinking that the traction is varying on the plus z plane and minus z plane and then integrate the traction over the surface, we could also think of the traction being the same everywhere on the z plane, and its value would be what it is at the center of the z plane. Okay. So, basically here the top face is the z plane, right, and then let us find out what is the traction at the center of this z plane. So, at the center, that is the center, and what is the coordinate here? So, the coordinate here, its radial coordinate is small r, the theta coordinate is theta, but the z coordinate is z plus delta z by 2, is not it, because r theta z is at the center of the cylindrical element and the top surface is at plus delta z by 2 up, is not it. So, this is at z plus delta z by 2. Likewise, on the negative z plane, the center of the negative z plane would be at r theta z minus delta z by 2, is not it. So, let us evaluate what is the traction on the top point, for example, here. So, what is the traction here? So, if I write here T on z plus, but at the center r theta z plus delta z by 2, that is simply sigma z z at r theta comma z plus delta z by 2 into E z, and you see the E z would be what it is at the center, because which coordinate has changed here? It is only the z coordinate which has changed. Z has changed to z plus delta z by 2. So, E z at the center of the z plane will be the same as what it is at the center of the cylindrical element. Okay. So, E z is the same as at the center of cylindrical element. All right. So, that is the first part, and then we have sigma z z is here, then tau theta z, that also evaluated at the center of the z plane r comma theta comma z plus delta z by 2 into E theta. Okay. And then E theta also does not change, because only the z coordinate has changed. Remember, E r and E theta change only if the theta coordinate changes. So, at the center of the z plane, E theta is what it is at the center of the cylindrical element. So, this value is also the same, E theta, and then the last one is plus tau r z, that also evaluated at r comma theta comma z plus delta z by 2 into E r, right, and E r again would be what it is at the center of the cylindrical element. Okay. So, the basis vectors here have not changed, because there was only a change in the z coordinate, right. All right. Likewise, we can also write down what is the traction on negative z plane. So, that is going to be traction on z minus. So, this is to be evaluated at r theta z minus delta z by 2, right, and all the traction components have to point in the negative direction here, because it is the minus z plane. So, this is then minus sigma z z of r theta z minus delta z by 2 into E z minus tau theta z of r theta z minus delta z by 2 into E theta minus tau r z of r comma theta comma z minus delta z by 2 times E r, and again the basis vectors are the same, they have not changed. It is only the component, the stress components which have changed, and that change is only due to change in the z coordinate. Now, think of this is the same traction everywhere on the plus z plane or on negative z plane. So, now we do not think of variation in the traction. Assume that the traction is constant and equal to the value of the traction at the center of the plus z plane and minus z plane. So, what will be the total force? You simply multiply this traction with the area of the z plane, is not it? And what is the area of the z plane? So, that is going to be r times delta theta into delta r, is not it? So, area of the z plane, that is small r into delta theta into delta r, right. Okay, very good. So, what would be then force on z plane for both plus and minus? So, if we evaluate the force on z plus the force on z minus, that simply traction on z plus at r theta comma z plus delta z by 2 plus the traction at z minus and r theta z minus delta z by 2 multiplied by the area A z, the area of the z plane, is not it? Now, we should think of doing the Taylor expansion. of Tz plus and Tz minus. But notice the way Tz plus is written, the stress components are changing only due to change in the z coordinate. Furthermore, the basis vectors have not changed here. So, when you do the Taylor's expansion, you only get the change due to change in z coordinate. So, you only have derivative with respect to z, is not it? So, what I mean is this one, for example, would be sigma z z at r theta z plus del sigma z z over del z at r theta z into delta z by 2, correct. Likewise, the bottom one, this one would be minus sigma z z at r theta z plus del sigma z z over del z at r theta z multiplied by delta z by 2, right. So, notice that the derivative term del sigma z z by del z has become positive, okay, just like it was happening earlier in Cartesian coordinate system. Now, when you add these two, you have sigma z z and minus sigma z z. So, they cancel out, and the derivative term is with delta z by 2 and it is the same. So, delta z by 2 into 2, it becomes delta z, right. So, can you see that only the derivative term survives here? So, that is going to happen when you do Taylor's expansion of tau theta z as well as of tau r z, right. So, finally, you will have del sigma z z over del z times E z plus del tau theta z over del z times E theta plus del tau r z over del z times E r, and then this has to be multiplied with delta z times A z, which together is the volume, right, delta volume, and then you have the higher order term plus small o of delta v. So, you see that in this approach, where we assume that the traction is constant over the z plane and whose value is same as the value of the traction at the midpoint of the z plane. So, with that approach, we got the same value as from the last class approach, where we also allowed the traction to vary over the z plane. So, this only tells us that the variation in the traction over the z plane, so that variation goes into small o delta v. So, contribution due to variation of traction on z plane is small o of delta v. Therefore, it did not show in our derivation, it is in this small o, okay, and we know that small o finally is going to cancel as you shrink the volume of the cylindrical element and divide by delta v, then small o of delta v by delta v goes to 0. So, therefore, the contribution due to the variation of traction over the planes does not matter here. Okay. So, when we have seen this, then we can work out the contribution due to the traction on positive E r and negative E r, as well as due to traction on positive theta and negative theta in the simpler approach, is not it? Because you remember the exact approach is quite tedious. So, we are going to avoid that, all right. Okay, so, let us now figure out what is the force due to traction on positive E r and negative ER plane. So, force due to positive ER plus the force due to negative R. We have to find out the traction on the positive R plane, but at the center of the positive R plane. Okay. So, where is the center of the positive R plane? So, that is at small r plus delta r by 2. Remember, the positive R plane is the outward plane whose r coordinate is small r plus delta r by 2, right. And then the theta coordinate at the center is same as the theta at the center of the cylindrical element. So, theta does not change, likewise z also does not change. So, what is changing here is the r coordinate, okay, multiplied by the area of the positive r plane. Okay. Now, can you see what is the area of the r plane? So, look at this picture, the area of the negative r plane, for example, what would be this area? So, that is the height, which is delta z, right, times this curved face or the curved line, and that is small r into delta theta. But here for the negative r plane, it is simply small r minus delta r by 2 into delta theta. And as the delta r, delta theta, delta z, as they go to 0, this curve will start looking like a straight line, and then what will be the area? That is simply the product of the sides. So, small r minus delta r by 2 into delta theta into delta z, right. So, that was for negative r plane. For positive r plane, you will have small r plus delta r by 2. Okay. So, basically here this is small r plus delta r by 2 into delta theta into delta z. So, that is the area. So, this thing is area of r plus the traction on negative r plane, but at small r minus delta r by 2 comma theta comma z into small r minus delta r by 2 into delta theta into delta z, right. So, that is the total force. So, we again here assume that the traction is not varying on the plus r plane or on negative r plane, it is a constant. So, therefore, we simply multiplied with the area of those planes. Okay. But now think of, we have to again do Taylor's expansion. Before that, we will have to expand t plus r and likewise t minus r. So, t plus r, when you expand it, so this is sigma r r at small r plus delta r by 2 comma theta comma z into E r. And you see, since here only the r coordinate is changing. So, E r again is what it is at the center of the cylindrical element, okay, plus tau theta r at small r plus delta r by 2 comma theta comma z into E theta plus tau z r at small r plus delta r by 2 comma theta comma z into E z. Okay. So, this whole thing is t on plus r plane at the center of the plus r plane. And you see again the basis vectors E r, E theta and E z would be the same as what it is at the center of the cylindrical element. So, when you do the Taylor's expansion, you will not have to do the Taylor's expansion of the basis vectors, you only have to do the Taylor's expansion of the components, right. And this then gets multiplied with small r plus delta r by 2 into delta theta into delta z, is not it. So, now let us just have a look at the first combination here. So, basically let us have a look at this combination. So, that is sigma r r at small r plus delta r by 2 comma theta comma z into small r plus delta r by 2, is not it. So, this is the thing which is changing. So, we have to do its Taylor's expansion. You see here we have sigma r r multiplied with r, and that r is also changing. Not only sigma r r is changing, but r itself. So, you can think of a function sigma r r into r and then do its Taylor's expansion, is not it. So, basically what I mean is, instead of doing the Taylor's expansion of only sigma r r, we will do the Taylor's expansion of the function sigma r r into r. So, this then becomes sigma r r into r, and this you evaluate at r theta z at the center of the cylindrical element, plus del by del r of sigma r r into r. You see we are doing the Taylor's expansion of the product, is not it, times the change in radius, which is here delta r by 2, and then you have also the higher order terms, and this gets multiplied with E r into delta theta into delta z, correct. All right. So, you see here it is the product which has to be Taylor's expanded. Let us further work it out. So, what does this become? This would be sigma r r into r plus del sigma r r over del r times r plus sigma r r. You have to do the differentiation of the product. So, you get two terms here. So, these two terms come from here, and then the whole thing is multiplied by delta r by 2 plus the higher order term into E r times delta theta times delta z, right. Likewise, you think of what would this combination would give me for negative r plane. So, for the negative r plane, we will have sigma r r at r minus delta r by 2 comma theta comma z times small r minus delta r by 2, is not it. And this comes with a negative sign for negative r plane into E r times delta theta times delta z, right. And again you can think of doing a Taylor's expansion. So, when you do the Taylor's expansion, you get sigma r r into r at the center of the cylindrical element. Then the derivative term, which comes with a minus sign here, minus del by del r of sigma r r into r, right, into delta r by 2, correct, times E r into delta theta into delta z, which you can also write finally as minus sigma r r into r plus del sigma r r by del r into r plus sigma r r, and then the whole thing is multiplied with delta r by 2 into E r into delta theta into delta z. Okay. And you see we now have to add the contribution on plus r and minus r, right. So, when you add, you see the sigma r r of r and minus sigma r r of r, they cancel each other, but the remaining terms remain. So, when you add them, what you get finally, that the force on plus r plus the force on negative r, that is equal to del sigma r r over del r into r plus sigma r r multiplied by delta r into delta theta into delta z, and of course, you also have an E r here, right. You know, we could also write this as del sigma r r over del r plus sigma r r by r. So, we take an r common, take it outside, into E r times r delta theta into delta z. But what is this combination here? That is nothing but the volume of the cylindrical element. So, that is delta V. So, we get an extra term here, sigma r r by r also. If this were Cartesian coordinate system, we would have simply gotten del sigma r r over del r into E r times delta V, but now we have an extra term. Anyway, this is only the contribution due to sigma r r. We also have tau theta r and tau z r. So, you can now think of what will they give. It is easy to figure out, is not it? So, that is going to be plus del tau theta r over del r plus tau theta r by r into E r into delta V plus del tau z r by del r plus tau z r over r into E z into delta V, right. Another physical reasoning for why we get an extra term here. So, you see these are the extra terms, is not it? In the Cartesian coordinate system, we only get the derivative term, but here we are also getting the extra term. Why is this happening? Is because in the cylindrical element, the plus r plane and minus r plane, the area of those two planes are not the same. For a cuboid element, the area of the opposite faces, they are the same always, right. But here, see, for the plus r and minus r, the area is different. Therefore, we get an extra term. For the plus z and minus z plane, can you recall that area is the same, is not it? Therefore, the contribution of the traction into total force gives us exactly of the same form as for the Cartesian coordinate system. You see, there is no extra term here. So, over here we do not have any extra term, but for the plus r and minus r, we get extra term because the area is not the same. Okay. So, that was for the r plane. Now, let us think of doing it for the plus theta and minus theta. So, we are now thinking of the theta planes over here. Okay. Again, we find out the traction at the center of the theta planes. So, what is the coordinate of a point at the center of the theta plane? So, any point at the center, for example, over here it has same r coordinate, but the theta coordinate is different now, it is theta minus delta theta by 2, and the z coordinate is now the same. So, the coordinate change is only in the theta coordinate. And then think of the traction, you have sigma theta theta e theta on this plane, you also have tau r theta e r on this plane. But the extra complication here is that the basis vectors are changing. See, the basis vector E r and E theta on negative theta plane is not the same as the basis vector E r and E theta on positive theta plane, because we know that E r and E theta change when the theta coordinate changes. So, therefore, we will get extra terms when we compute the force even for theta planes, just like we got extra term for r planes, but the reason was different there because the area was different, but here because the basis vectors are also changing. So, we will get extra term. For the plus theta and negative theta, the area is the same, which is delta r into delta z, right. So, we can write here that the area A theta is simply delta r into delta z. All right. So, let us work out the derivation for the force on theta planes. So, the force on plus theta plus the force on negative theta. So, it has the traction on plus theta plane. So, traction on plus theta plane, but we have to evaluate it at the center of the plus theta plane, which is at r comma theta plus delta theta by 2 comma z, right, plus the traction on negative theta plane, and that has to be evaluated at r comma theta minus delta theta by 2 comma z, and this whole thing has to be multiplied with the area of the theta plane, which is same for plus theta and minus theta, and that is equal to delta r into delta theta. All right. And now, we have to think of doing the Taylor's expansion. So, let us think of for the t plus theta first of all. So, t plus theta is sigma theta theta at r comma theta plus delta theta by 2 comma z into E theta, but E theta also at theta plus delta theta by 2. See, because E theta is also changing, plus tau r theta at r comma theta plus delta theta by 2 comma z into E r, but E r has also changed. So, E r at theta plus delta theta by 2, okay, plus tau z theta at r comma theta plus delta theta by 2 comma z into E z, but E z there is no change, E z is independent of change in theta coordinate, is not it. So, E z does not change. So, we could write here that these two they are changing, with theta. Okay. So, we will have to then do the Taylor's expansion. So, when you work out the Taylor's expansion, we will get sigma theta theta into E theta at the center plus the derivative term, right. And here, because sigma theta theta and E theta both are changing, so we will have to take the derivative of both of them, is not it, and we can do it together. So, we would say it is plus del by del theta of sigma theta theta into E theta times delta theta by 2 plus the higher order term. Okay. Likewise, for the next one, we will have plus tau r theta into E r at the center of the cylindrical element plus del by del theta of tau r theta into E r times delta theta by 2, right, plus dot dot dot. And the last one, it is only changing due to the change in stress components, E z is not changing. So, it is simply tau z theta into E z plus del tau z theta by del theta into delta theta by 2 times E z. Okay. Likewise, you can think of the contribution due to the negative theta plane, right, and when you do the Taylor's expansion. So, the traction on negative theta plane, that comes with a minus sign here, minus sigma theta theta E theta, correct, but the derivative term become positive because you have a minus sign into minus delta theta by 2. So, minus minus becomes plus. So, this is plus del by del theta of sigma theta theta E theta into delta theta by 2 plus dot dot dot, right. Likewise, you can think of the other terms here, and notice again when you add, these are cancelling. So, what is the total force then? Total force on plus theta and minus theta. So, that is going to be del over del theta of sigma theta theta E theta times delta theta plus del of del theta of tau r theta E r times delta theta plus del of del theta of tau z theta times delta theta, and the whole thing is multiplied with the area of the theta plane, which is delta r into delta z. Okay. And can you now see where are the extra terms coming from? So, the extra terms come because we also have to take the derivative of E theta and E r. Each of the first two terms give us two terms. So, this one for example gives me del sigma theta theta over del theta times E theta plus sigma theta theta into del E theta by del theta, and recall it from our last class, that was simply minus of E r, is not it. So, this becomes minus of E r, correct. So, you get two terms here. Likewise, here this gives us del tau r theta by del theta into E r plus tau r theta into del E r by del theta. So, plus tau r theta into del E r by del theta, and that is simply E theta. Then you have the last one, into delta r delta theta delta z. And if we divide by r and multiply by r, then we know that this thing here is simply the volume of the cylindrical element. Okay. And what are the extra terms? So, this and this here, these two are the extra terms. All right. So, once we have found out the force due to tractions on all the 6 faces of the cylindrical element, we simply have to add them together and get the total force, is not it? So, let us try to do that. So, the total force due to traction. So, we first started with the plus z plane and minus z plane, and recall that it had 3 terms, right. So, I am just going to write it here, del sigma z z by del z E z plus del tau theta z by del z E theta plus del tau r z by del z E r, and the whole thing is multiplied with the volume, that is everywhere. So, we will write them separately. So, this is just the plus z and minus z, then for plus r and minus r, and so you have to recall it, that is right here with the extra terms. Okay. So, we will write it here. So, we get del sigma r r over del r plus sigma r r by r into E r plus del tau theta r over del r plus tau theta r by r into E theta plus del tau z r over del r plus tau z r over r into E z. Okay. And then for the plus theta and minus theta, which we have right here, and we can write it here also, plus 1 over r of del tau r theta over del theta minus sigma theta theta into E r. So, look at the 5 terms, and what are the components in E r direction. So, in the E r direction, you see this and this, these two are the components in the E r direction. So, we simply club them together. Okay. And then for E theta, we have plus 1 over r tau r theta plus del sigma theta theta over del theta multiplied by E theta, and finally, for E z we have del over del theta of tau z theta times E z, okay, and the whole thing has to be multiplied with the volume of the cylindrical element. So, that is the total force due to traction. I will just group them. So, this is due to z plane, these are due to r plane, and finally, these are due to theta plane. this is only the traction force. You know, on the cylindrical element we will also have the body force, is not it? Okay. And the body force, can you recall from the Cartesian coordinate system, the body force we simply have to find out at the center of the element multiplied with the volume of the element. Here also we can simply have the body force at the center of the cylindrical element multiplied with the volume plus the higher order in volumes, small o of delta V. Okay. And let us think of decomposing the body force not along E 1, E 2, E 3, but along E r, E theta, E z. Okay. So, the force due to body force would simply be B r E r plus B theta E theta plus B z E z multiplied with the volume of the cylindrical element, all right, plus the little o of delta V, of course, it is everywhere, and that has to be equal to rho times acceleration. Remember, rate of change of linear momentum. Luckily, these terms do not change when we work out even in the cylindrical coordinate system. So, the right hand side, so basically d by dt of p, that simply becomes rho times a r E r plus a theta E theta plus a z E z. So, we have decomposed the acceleration along E r, E theta and E z, okay, multiplied by delta V plus little o of delta V. So, now we have everything actually. So, can you see that traction force is also multiplied with delta V, body force is also multiplied with delta V, and rate of change of linear momentum is also multiplied with delta V. So, we simply divide by delta V in the Newton's second law and take the limit as delta V goes to 0, just as we were doing for Cartesian coordinate system. So, when you do that, the small o of delta V terms, they all cancel out, and then finally, we will have the terms which are explicitly shown here, is not it? Can we think of clubbing them along E r, E theta and E z direction, so that we get the equations in the r direction, theta direction and z direction separately. So, what we will have to do is simply for the E r just extract the components which are in the E r direction, right. So, let us look at the components in the E r direction. So, you can actually see it here. So, this is the component along E r, this is also the component along E r, and then this is the component along E r, and likewise for the body force and the rate of change of angular momentum. So, this means the equation in r direction, so that is going to be del sigma r r over del r plus del tau r theta over del theta, and this comes with plus 1 by r also, plus del tau r z over del z, and then we have extra term which is sigma r r minus sigma theta theta over r plus the body force B r is equal to rho times acceleration in the r direction. Okay. So, you see we get an extra term here, sigma r r minus sigma theta theta by r. The first three terms are very similar to what we get in the Cartesian coordinate system. You see, first one is del sigma r r by del r. First of all, each of the stress components, since this is the r direction equation, we look for the stress components in the r direction. Therefore, we have sigma r r, tau r theta and tau r z, and then we take the derivative with respect to second index. Therefore, it is del by del r, del by del theta and del by del z. And whenever we do del by del theta, we have to accompany it with 1 by r, okay, because the derivative has to be with respect to length and theta is non-dimensional. So, we multiply with r to make it of the order of length. Okay. Therefore, wherever we have the derivative with theta, it has to be accompanied with 1 by r. Okay. So, I can simply write here the derivative in theta are accompanied with 1 by r, okay, and this is of course the extra term. See, it was really important to work out the derivation. If you had thought that okay, why don't we simply write down the equation as in the Cartesian coordinate system, this would have never come up, isn't it? So, it is important to work out the derivation explicitly in cylindrical coordinate system. Similarly, you can also write down the equation in theta direction. And the equation in z direction. So, they will have first of all the usual terms, the ones that arise in Cartesian coordinate system. So, for theta direction we have to look for all the traction components in theta direction, which are tau theta r, sigma theta theta and tau theta z. Okay. So, this becomes del tau theta r over del r plus 1 by r del sigma theta theta over del theta. See, again the derivative with theta is accompanied with 1 by r plus del tau theta z over del z. So, these are the usual terms, and we will of course look for the extra terms. Then we have b theta is equal to rho times acceleration in theta direction. Likewise, for the z direction we have all the traction components in the z direction. So, the first term becomes del by del r of tau z r plus 1 over r del by del theta of tau z theta plus del sigma z z over del z. So, these are the usual terms. We will also have extra terms which we will explore, plus b z is equal to rho times acceleration in the z direction. Okay, now, look for the extra terms for the theta direction. So, we have to come back here and see what are the extra terms in theta direction. So, this is the theta direction which has already been taken into account. Okay, so, you see this is the extra term which has not been taken into account, and this is also the extra term which has not been taken into account. So, there are two extra terms which we have not written down, tau theta r and tau r theta, but we know that because stress is symmetric. So, tau theta r is same as tau r theta. So, it simply becomes 2 times tau r theta over r. So, the extra term here is plus 2 times tau r theta over r. All right. Let us look for the extra term for the z direction. So, for the z direction here, the first term here this is usual, then look here, this is the extra term tau z r by r. So, that is something we have not taken into account. So, we will write here plus tau z r over r, all right. So, now we have the equation for the cylindrical coordinate system with these extra terms also. Okay. So, this completes our derivation for the linear momentum balance in cylindrical coordinate system. In the next class, we will see how does the strain matrix look like in the cylindrical coordinate system. Just like this is the equations of equilibrium in the cylindrical coordinate system, we will look for the strain matrix in the cylindrical coordinate system, all right. So, see you in the next class. Thank you.